this whole section is about something called a limit. And it's easy later in the class to focus on derivatives and a lot of words that get thrown around in calculus, but limits are a big part of calculus. They're a big part of how we describe the world in the physical and natural sciences, as well as in statistics. That calculus isn't just derivatives. Limits are actually really crucial as well. And if you care about communicating, which you should be caring about, you should care about limits. They really let us talk about complicated things that people like Zeno were having a hard time talking about. So let's go back and recall this fun function, y equals x squared. And we said, all right, if we have a point 1, 1, and we want to know the slope of a secant line connecting 1, 1 to x squared, y x squared, because if I plug in x for my x, then my y is x squared. So that's my x and my y coordinate as long as I am on this fun curve here. Okay. So for any x value, I know what the y value is. I want to know the slope of the secant line. Well, that's just going to be, let's write this down. Slope of the secant is going to be the change in the y values. So it's x squared minus 1, x squared and 1, and over the change in the x values, x minus 1. Okay, and oops, clean this up a little bit here. And this worked really well in almost all cases, right? That this would actually give me the slope of that secant line as long as I didn't plug in a 1. If I plugged in a 1 for x, that denominator would become a 0. So the tangent, the slope of my tangent line is basically what happens when x is going to 1. Like what happens when x gets really close to 1, but I can't plug it in, right? So the way we're going to write this in just a minute is going to look like this. It's the limit, lim, as x goes to 1, that's a fun arrow, of this equation here. Okay. And that's this fun notation just saying, is there some behavior? Is there a trend that actually happens that we can encapsulate by saying, well, when x gets really close to 1, it's converging to a number. And in fact, if I were to try to graph x squared minus 1 over x minus 1, if I was going to graph that, it looks a little bit like this. I'll graph it down here. It looks like this fun line, with a hole right there at 1. And everywhere else it just looks like a line. And if I was going to ask you, hey, what should I fill in that hole with? I'll give you some scale here too. 2. What should I fill in that hole with? Well, once you look at it like this, it's pretty clear what that hole should be filled with. What is happening as this line gets closer and closer to that hole? And the answer is 2, which is exactly what we got before by looking at some charts. Okay, so a limit in really layman's terms is just saying, hey, if there's a hole, fill it, right? If there's no hole, well, then you can probably just plug in. I'm going to go ahead and even show you what we're going to do in a minute, and more so in future sections, how we're going to deal with this, not by graphs, or not by tables, but really soon we're going to deal with this by algebra. You may have noticed that that this simplifies. So this x squared minus 1 factors. Once you realize that those factor, you might realize you should be able to cancel out those factors. Now, you can absolutely cancel out those factors unless x equals 1. I'm not allowed to cancel out 0 over 0. So for all values except x equals 1, I can cancel these out. And we'll talk more about that in the future. But then this just becomes the limit as x goes to 1 of x plus 1. That's this graph over here, x plus 1 with a little hole right there. But in the limit, that is just going to be 1 plus 1 equals 2. Okay, I don't want to scare you too much. I just wanted you to see where this is going algebraically as well as graphically right from the beginning. So everything we're going to do, we're going to have both a graphical interpretation, we're going to have an algebraic interpretation, we might have an interpretation using tables of numbers, and I want you to get that right from the get-go. There isn't going to be just one right way to do this. But our motivation right now is going to be trying to find slopes of tangent lines. Our motivation in math as a bigger topic is much, much bigger than slopes of tangent lines for a limit. They show up all over the place. Okay, we are at that magic point. Let's talk about the definition of a limit. So here's how we write it. It's a limit as x goes to a of some function f of x equals L. So often, remember, f of x is going to just be your y. When we have functions and we want to graph them, we say, oh yeah, y equals f of x. Okay, and L is just going to be some number. So back here, that L was a 2. Or you could have seen it up here because we plugged in and we got a 2 for that value. And this a was this 1, that x value we're getting really, really close to. And f of x is some function. In this case up here, that function was x squared minus 1 over x minus 1. And in words, we see that the limit of f of x as x approaches a is L. And that's how we kind of say all of that in words. And we'll say, oh yeah, the limit of f of x is L as x approaches a. What we want to think about when we say that, jumping down to what it means, number 2, is as x gets really, really close to a, what is happening to f? Okay, what is happening to your y value as x gets really, really close to up here to 1? What's happening to the y value as we get really, really close? But in a limit, we don't need to worry about plugging in. We're just worrying about the behavior nearby. The limit is actually blind to that hole. It's blind to that one spot in the domain. Okay, so what it means, this first one, is that we can force f of x, we can force our y values to be arbitrarily close as we want, in this case to 2, by just making sure that x is close to a, but not equal to it. So I say, hey, the limit as x goes to 1 is 2, and what I mean by that a little more mathematically is as close as you want it to be, you want it to be within 0.1, I can give you an x value, I can give you a range of x values here that would force my y values to be within 0.1 of 2. However close you need it to be, we can force it to be that close. And this is what we mean by convergence. Okay, that was a lot. That might even be worth pausing and going back over. But what we want to get from this, first off, is notation. Because you're going to use this notation, you're going to read it. To recognize how to say this, x is getting close to a, x approaches a is the better way. The limit as x approaches a of f of x equals L. What does that mean? Well, in pictures, it means that there's going to be probably some kind of a hole that needs to be filled. A little more algebraically, it means that as close as you want f of x to get to y, we just need to zoom in close enough, right? If we zoom in, it's going to get closer and closer to that y value that we want. Okay, as close as you want it to be. It should not be bouncing all over the place. Whew, a lot of words. Worth kind of seeing, can you say this to yourself? One of the joys of videos is that I can go a little faster and count on you to pause, replay, take some notes on your own. So let's go in an unconventional fashion. Let's go to pictures first, and then we'll go back to algebra. What does a limit look like? And I think this might be one of the better ways to let this sink in. Let's write down a question here. What is the, we'll number these. What is the limit as x goes to 1 of f of x? So in pictures here, sorry about that. Let's do x goes to 2. That'll be a better one to start with. In pictures here, this x value is 2, and we're saying what is happening to that y value. And as we get really, really close to 2, I've included this open circle here, which means it's not in the domain, or rather that point is not part of the graph, but it sure does look like that y value is a 1. Okay, so I'm just reading off where is this open circle. What's the y value of that open circle? Let's do another one. Looks like this next one is 1, 2, 3, 4, 5. So the limit as x goes to 5 of f of x. Now we've got a new little wrinkle here. It looks like I have an open circle right here at y equals 2, but my function value is actually a 1. My function is defined on this closed circle. Kind of a rare situation that we see functions defined like this, but it's worth seeing that, hey, I've got this open circle here, the function's getting really close to this open circle, but the actual function value at 5, 1, 2, 3, 4, 5, is 1. Now, the limit, maybe it's worth thinking if you know the answer here. It's probably either going to be -2 or 1. It might be worth saying, which do you think it is? I'll wait. Okay, and here is your answer. That limit looks on the domain, looks on these x values really close to 5. But that limit is always going to ignore the number 5. It does not care whatsoever what that function does at 5. Doesn't even see it. And so that limit here is going to be -2. Okay. And that's what we want, right? We don't want, we want that limit to not see places where we might be dividing by 0, which is going to be at that one particular spot. Okay, we got a couple more things to work out on this picture here. We'll do a 3 and a 4. So these limits are going to be, this was 5, 6, 7, sure. So the limit as x approaches 7, just to help you out, here's a little 7 down here. And we're going to do a limit as x approaches 9. And again, these are going to be f of x, f of x. Use a y if you want there, but I'll mainly be writing f of x for our function notation. Okay, worth seeing if you can do these on your own. I'm going to jump right into them. Okay, for the 7, we're right up here, and we're asking what is happening to our y values as x gets really close to 7. This might be one of those deceptively easy questions. Nothing special is happening to our y value there, right? Our x value, as we change our x values, it's this nice smooth curve. It's connected the whole way. And so our y value is just going to be the value of the function, right? I could put an open circle there if I wanted to, but I really don't need to. It's just going to be 2. That's the y value right there at 7. Because there's nothing weird going on with that function, the word that we're going to have in a section or two is continuous. And I hope you've heard that word before. This function is continuous at 7. There's no holes, there's no jumps, there's no asymptotes. And when it's continuous, you really can just plug in. You can just read off the value from the function. And in fact, that is going to be our definition of continuous in a section or two, is a function will be continuous at 7 if you're allowed to read out, if the limit agrees with the function. Okay? Or in other words, there's no holes or jumps or asymptotes. Okay, so that one was nice. Nice continuous curve right there. One more, which is really representing a much bigger case. Okay, so as we get to 9, we're at this discontinuity. As we come in from the left, it looks like we're going to 3. As we come in from the right, it looks like we're going to -1. Which leaves us with a bit of a dilemma. Should it be -1? Should it be 3? Maybe you want to average them and make it 2. But because of that ambiguity, we are going to actually say none of them. We're going to say it does not exist. So the way we abbreviate that is DNE. Does not exist. Or you can write the words. Or does not converge is also okay. So this will happen plenty. And the easiest way, if you want an example of something that does not, where the limit doesn't exist, just look at something with the jump, right? Or even a vertical asymptote would do that. And the reason, again, is just because as we come in from the left, it doesn't agree with what we get when we come in from the right. And so if the function doesn't have one behavior, one number it's converging to, one capital L, then we're going to say that limit doesn't exist. And a good portion of the rest of this chapter is actually going to be what are some ways we can still communicate what's happening? Because again, limits are really valuable in communicating. If Zeno had a limit, he might be able to have resolved his own paradoxes.